In the last decades of the 19th and the early 20th century, the fundamental understanding of the material world underwent radical change. What had previously been considered an indivisible atomic unit became the object of detailed scientific investigation, new methods appeared, refined experiments were conducted, and fundamentally different questions were posed about where and how the energy of matter is stored. These discoveries laid the foundation not only for peaceful science but also for the most powerful technological transformations, the consequences of which humanity would feel in the 20th century. The story we begin today is the story of the intersection of pure science and political realities, a story of ideas that, having arisen in laboratory conditions, received functional embodiment in large-scale engineering projects. We will speak about nuclear physics, about the first experimental evidence of atomic nucleus fission, and about how successive discoveries led to the realization of the possibility of a controlled chain reaction, the principle underlying both nuclear power and nuclear weapons. It is important to emphasize, this is not about technical instructions or engineering details, but about the scientific prerequisites and the intellectual path followed by the researchers. We will trace how, step by step, an understanding of the structure of the atom took shape, how the discovery of the neutron and subsequent experiments made possible a fundamental notion: the nucleus can not only change its state but also split, releasing energy in an amount comparable to the best emerging energy sources of the time. This story is also about people, scientists who, in the quiet of laboratories, recorded anomalies in spectra and decay products about those who saw in the results not only scientific interest but also strategic implications. The migration of scientists, international exchange of knowledge, and the tensions of the era, all this heightened attention to research and stimulated the concentration of resources and ideas in rare but key centers of science. In the next part, we will examine in detail the key discoveries and experiments, from observations that initially baffled scientists to a coherent theory of nuclear fission and the posing of the question of a chain reaction. We will pay attention to the critical publications and indicators that ultimately formed the technical and intellectual platform for further developments in nuclear physics. This material is designed for thoughtful perception. We will rely on documentary evidence and the chronology of events to give a clear picture of how a scientific idea became politically significant and technically feasible. Our goal is not only to reconstruct the facts but also to show the logic of the transition from the discovery of a natural phenomenon to the realization of its large-scale consequences. As we proceed, we ask that you pay close attention to details. Many key points in this story are not obvious at first glance, but they are precisely what determined the subsequent course of events. Ahead lies a chain of discoveries, personalities, and decisions, the culmination of which in 1945 was events that changed the face of the world. At the end of the 1930s, scientific discoveries in nuclear physics ceased to be exclusively an academic problem and acquired a pronounced military-political significance. The main turning point was not so much a single experiment as the realization of the possibility of the rapid release of a colossal amount of energy during the fission of heavy nuclei and the fact that this phenomenon could, in principle, be used to create a weapon of unprecedented destructive power. However, for the idea to turn into a political task, a signal was required, a document or action capable of forcing government structures to pay attention and allocate resources. Such a signal was the letter prepared by Lou Szerd and signed by Albert Einstein in August 1939. Szerd, a Hungarian physicist who had fled fascism, understood the technical essence of the problem and the danger that the same path could be pursued by aggressive powers. He persuaded Einstein to sign a letter addressed to U.S. President Franklin Delano Roosevelt, which set out the grounds for a serious state scientific initiative. It described the possibility of creating a bomb based on uranium, noted the need to acquire uranium ore, and proposed coordination of efforts. The letter is dated August 2, 1939. It did not contain detailed technical guidance but clearly formulated the strategic dimension of the problem, a potential that could not be ignored. The response of the American administration was measured yet prompt. Roosevelt ordered the issue to be studied, and under the leadership of Vannevar Bush, then the head of the Office of Scientific Research and Development, a committee of advisors on uranium was created at the National Bureau of Standards. In 1940-1941, meetings were held, reports and assessments were prepared, and a bureaucratic infrastructure was formed for interaction between scientists, industry, and government. The political weight of the letter was explained not only by Einstein's name as a public authority but also by the specificity of the concerns. In the context of the European War, the idea that Germany might obtain such a weapon sounded like a direct challenge. Parallel to American discussions, the British scientific initiative played an important role. In 1940-1941, British researchers working under wartime conditions organized the MAUD Committee, a group that assessed the practical feasibility of nuclear weapons. Their report, completed in 1941, concluded that creating such a weapon was technically feasible and would require significant industrial effort but could be achieved within a foreseeable timeframe. This report carried great political weight. It confirmed to U.S. authorities that the topic was not a purely scientific hypothesis but a real military prospect. One of the key political effects was the transfer of the scientific discussion into the realm of state priority. In early 1942, the U.S. administration decided to create a large-scale, secret program under military control and funding, the Manhattan Project. This decision was the result not only of scientific arguments but also of political logic. Wars require accelerated technological solutions, and the state is ready to mobilize resources to develop potentially decisive weapons. For politicians, concrete steps were important: obtaining access to uranium ore, including supplies from the Congo, controlling research, protecting secrecy, creating production infrastructure, and coordinating between scientific centers and the military machine. The political signal also had another side, moral and socio-political. By signing the letter and becoming involved in the project, a number of well-known scientists inadvertently turned into active participants in state strategy. This gave rise to complex dilemmas. Military and political leaders saw in nuclear research a chance to hasten the end of the war and gain an advantage, while the scientists themselves faced questions of responsibility for the consequences of their discoveries. The public sphere remained mostly in the shadows. The project was kept in strict secrecy, which excluded public discussion of risks and alternatives. Finally, the political signal also meant international competition of ideas and resources. Issues of ownership of knowledge, control over materials, and diplomatic relations with allies all became part of the operational agenda. Even the decision about which countries and scientists would be involved, the British, the Canadians, migrants from Europe, had a political tint and was dictated not only by scientific benefit but also by considerations of security and trust. Thus, the political signal was not a single document and not only the fear of a possible success by the enemy. It was a chain of decisions and institutional reactions, from the Sillersteinstein letter and the work of expert commissions to the creation of a secret state program, the mobilization of industrial resources, and the elevation of a scientific problem to the rank of a priority military task. This stage determined the scale of the project, the resources, organizational structure, and level of secrecy that subsequently made possible both the development and the industrial embodiment of nuclear weapons during the war years. By early 1942, the question of the military use of nuclear energy had definitively moved beyond scientific hypotheses and became the subject of state decisions. The Sillersteinstein letter, the British MAUD Committee's reports, and the expert conclusions of U.S. commissions clearly indicated that the possibility of creating a weapon based on nuclear fission required the immediate concentration of efforts. It was at this time that the Manhattan Project emerged, the largest secret program of the wartime era, which united fundamental science, industry, and military administration into a single system. The project's name is linked to the location of the first headquarters of the U.S. Army Corps of Engineers in Manhattan, New York. A formal decision to begin full-scale work was made in 1942, when President Franklin Delano Roosevelt gave the go-ahead for implementation under military control. The project's leader was General Leslie Richard Groves, known as a tough administrator and experienced organizer who had built a number of strategically important military facilities during his career. He was entrusted with controlling resources, timelines, and security. Scientific leadership was assigned to J. Robert Oppenheimer, a theoretical physicist whose ability to bring people together and build scientific teams was recognized as outstanding. Despite not having previously held administrative positions of such scale, Oppenheimer managed to gather around himself the best specialists in theoretical and experimental physics. From the outset, the Manhattan Project was marked by unprecedented scope. More than 130,000 people worked within it: scientists, engineers, chemists, military personnel, and tens of thousands of workers who ensured the functioning of huge plants and laboratories. The program was distributed across numerous sites, each performing strictly defined tasks. In Los Alamos, New Mexico, under Oppenheimer's leadership, the main theoretical research, calculations, and the design of the future weapon were conducted. Leading physicists of the time were concentrated there, many of them migrants from Europe who had fled fascism. In Oak Ridge, Tennessee, uranium enrichment was undertaken. Colossal factories, requiring enormous energy capacities, extracted the rare isotope uranium-235 from the natural mixture. In Hanford, Washington, reactors and processing plants were created to produce plutonium, a new artificial element that was also to become the basis for a weapon. Additionally, dozens of auxiliary laboratories and industrial facilities were established across the country, performing specific tasks in metallurgy, chemical processing, and precision engineering. The secrecy of the project was unprecedented. Workers and engineers at the facilities often did not even suspect the ultimate goal of their labor. Information was strictly compartmentalized, each person worked on their own part of the task without knowing the whole picture. Access to sites was strictly controlled, and the correspondence and movements of employees were monitored by the military. As a result, many participants realized the true scale of what was happening only after the war ended, when the details of its outcomes became known. The financial costs of the Manhattan Project were also staggering. The program's budget amounted to about $2 billion wartime U.S. dollars, which is equivalent to tens of billions in today's prices. These funds went into building unique industrial complexes, ensuring energy supply, purchasing rare raw materials, and paying specialists. The program required the mobilization of the country's industrial capacities and, in some cases, international cooperation. Allied support, for example, made it possible to secure access to strategic reserves of uranium ore from the Belgian Congo. The organization of the work combined strict military discipline with a relative freedom of scientific inquiry. General Groves set deadlines, controlled secrecy, and allocated resources, while Oppenheimer and his colleagues sought the opportunity to conduct open discussions and exchange ideas within the scientific collective. This did not exclude conflicts. Scientists strove for intellectual freedom. The military demanded unquestioning obedience and adherence to regulations. Yet it was precisely this tense equilibrium between army discipline and scientific initiative that made the project viable and allowed thousands of people to unite their efforts toward a single goal. The international contribution was also significant. British researchers, who had begun similar developments earlier, transferred their work to the Americans within the framework of Allied cooperation. Many migrants from Europe were involved in the project. Enrico Fermi, John von Neumann, Edward Teller, Niels Bohr, and other world-class scientists contributed invaluable expertise and knowledge. This gave the Manhattan Project the features of a truly international scientific enterprise, although it remained under full U.S. military control. The creation of the Manhattan Project was not merely an administrative decision during wartime. It marked the transition of science to a new level, from university laboratories and academic discussions to a vast centralized system where research was subordinated to state interests and regarded as a strategic resource. The project formed a new model of interaction between science and the state, a model that later determined the development of many programs in the second half of the 20th century, from nuclear power to space exploration. In just 3 years, from 1942 to 1945, scientists and engineers, working under conditions of secrecy and deadline pressure, moved from theoretical calculations to the creation of a weapon that changed the course of world history. When the Manhattan Project was officially approved in 1942, one of the first tasks was to define the leadership system and distribute functions among the numerous centers. The outcome of the program depended on how the work would be organized. Too much required coordination, from the mining of raw materials and chemical processes to the development of the most complex physical models and the construction of the final product. That is why the project received dual leadership, military and scientific. At the head of the program stood General Leslie Richard Groves, a man whose career had previously been associated with the construction of major defense facilities, in particular the Pentagon. Groves had a reputation as a tough administrator inclined to authoritarian methods, yet exceptionally energetic and effective. His main tasks were control over timelines, allocation of resources, coordination of industrial enterprises, and ensuring secrecy. It was Groves who succeeded in giving the project, whose cost ultimately exceeded $2 billion, priority in financing and supply even under wartime conditions. He operated skillfully in Washington, obtained approvals at the highest level, and, despite resistance from some officials, succeeded in creating a system in which thousands of employees and dozens of organizations were subordinated to a single goal. Scientific leadership was entrusted to J. Robert Oppenheimer. At the time of his appointment, he was only 38 and had no experience working in administrative structures of such scale. Nevertheless, the choice proved successful. Oppenheimer possessed a unique ability to unite people and create an atmosphere of intellectual inquiry in which the finest minds could work with maximum productivity. His authority as a scientist and his charisma as a leader made it possible to assemble in Los Alamos a team of world-class physicists. Among them were Hans Bethe, who headed the theoretical division, Enrico Fermi, responsible for experimental work and reactors, Richard Feynman, who handled calculations, and many other specialists. Notably, many were migrants from Europe who had fled fascist regimes and thus viewed the project not only as a scientific task but also as a personal mission. Los Alamos became the brain center of the Manhattan Project. This closed city in the New Mexico desert, created virtually from scratch, turned into a place where the main theoretical calculations and design work were carried out. Here, explosive device schemes were modeled, hypotheses about neutron behavior were tested, critical masses were calculated, and the first prototypes were developed. Los Alamos had a special atmosphere, on the one hand, strict security and isolation on the other, an intense exchange of ideas within the collective. Scientific seminars and joint discussions were an essential part of the work, and it was precisely there that decisions were born that determined the project's future. But theory alone was not enough. The Manhattan Project relied on a network of laboratories and industrial complexes, each performing its own function. In Oak Ridge, Tennessee, the task of uranium enrichment was concentrated. Natural uranium contained only about 0.7% of the isotope uranium-235 needed for weapons. Separating this isotope from the heavier uranium-238 required colossal effort. Entire plants with gas diffusion systems and electromagnetic separation were built. These processes were so energy-intensive that individual installations consumed more electricity than large cities. Nevertheless, it was in Oak Ridge that the necessary amount of uranium for one of the bombs was obtained. Equally important was Hanford in the state of Washington. There, the first industrial reactors for producing plutonium-239, another fissile material, were built. The chemical reprocessing of irradiated uranium blocks made it possible to extract plutonium, and it later became the basis of the second bomb. Hanford was a grand engineering enterprise, reactors, cooling systems, and chemical laboratories, all created under conditions of the strictest secrecy and record timelines. In addition to these centers, there were dozens of auxiliary laboratories and plants engaged in specific tasks: metallurgy, the production of explosives, the development of detonation systems, and precision mechanics. For example, the metallurgical laboratory in Chicago, headed by Arthur Compton, played a key role in the first experiments with a chain reaction. It was there in 1942 that Enrico Fermi conducted the first controlled nuclear reactor experiment, proving the possibility of a controlled chain reaction. This event became a milestone, confirming that the program was moving in the right direction. Thus, the leadership and laboratories of the Manhattan Project formed a highly complex system in which military discipline was combined with scientific inquiry, and secrecy coexisted with the need for knowledge exchange within the collective. General Groves provided the organizational foundation, resources, and security. Oppenheimer created the intellectual climate and united the best specialists. Los Alamos became the project's scientific symbol, Oak Ridge and Hanford its industrial giants, and Chicago and other laboratories important hubs of experiments and testing. This entire network operated as a single organism, and it was thanks to its coordinated work that within a few years scientists and engineers moved from theoretical calculations to creating a weapon that changed the course of world history. One of the key challenges of the Manhattan Project was determining exactly how to realize an explosive chain reaction in fissile material. The theoretical basis was known. When a critical mass of uranium-235 or plutonium-239 is reached, an avalanche process of fission begins, accompanied by the release of colossal energy. But turning this principle into a real weapon required an engineering solution that would ensure the instantaneous and complete engagement of the material in the reaction. It was here that two different approaches were born, each with its own advantages and difficulties. The first option received the name gun-type scheme. Its essence lay in using a mechanical device to bring together two subcritical parts, two portions of a uranium charge, into a single hole. When they collided at high speed, a critical mass was formed, and the reaction began almost instantly. This scheme was relatively simple to understand and calculate, and therefore it was chosen for work with uranium-235. The main limitation was the scarcity of uranium-235 itself. It had to be obtained through a very complex enrichment process at Oak Ridge. However, the weapon's design itself seemed reliable enough to warrant confidence in success without preliminary testing. The second approach was more complex, the so-called implosion scheme. It was intended for the use of plutonium-239 produced in the reactors at Hanford. The problem was that plutonium contained isotopic impurities prone to premature fission, which made the gun-type scheme unreliable. The reaction could begin too early and fail to produce the desired effect. To overcome this difficulty, the idea of implosion was developed. Its essence was the symmetrical compression of a plutonium core using high explosives surrounding it on all sides. As a result, there was a sharp reduction in volume and an increase in the material's density, which ensured the attainment of a critical state in a negligibly short time. The implosion scheme proved to be a true engineering challenge. It required the most precise calculations, the development of systems for the synchronized detonation of numerous detonators, and thorough checking of each component. For this, separate groups were created in Los Alamos devoted exclusively to the theory of explosions, practical tests of mock-ups, and mathematical modeling. Many scientists initially doubted the feasibility of its implementation, but under conditions of limited time and resources, risks had to be taken. Thus, the Manhattan Project followed two parallel paths. Uranium-235 was used for the gun-type design, relatively simple but dependent on a rare material. Plutonium-239 was used in a more complex implosion scheme that required many experiments but offered the possibility of obtaining a significantly greater explosive yield. Ultimately, both concepts proved viable. The first was embodied in the bomb Little Boy, the second in Fat Man. These two engineering approaches became the central technological core of the Manhattan Project and determined the course of its further testing and application. One of the most labor-intensive and strategically complex stages of the Manhattan Project was the production of fissile materials. Theoretically, it was known that two substances are suitable for creating nuclear weapons, uranium-235 and plutonium-239. But in nature their amount is either negligible or they are not present in a ready-made form at all. Therefore, the tasks of mining, enriching, and processing these substances became the heart of the program, requiring colossal resources and the creation of entirely new branches of industry. Natural uranium consists almost entirely of the isotope uranium-238, which cannot sustain a chain reaction in pure form. Only about 7 atoms out of 1,000 are uranium-235, suitable for weapons. This meant that to obtain even small amounts of uranium-235, huge masses of ore had to be processed. The problem was that isotopes cannot be separated by chemical methods. They are identical chemically and differ only in mass. This is why several parallel installations using physical separation methods were created at Oak Ridge, Tennessee. The most large-scale were electromagnetic separation and gas diffusion. These processes required incredible amounts of energy. Entire power plants worked solely to supply the enrichment facilities. But it was there that the first batches of uranium-235 were obtained, which were subsequently used to create the uranium bomb. In parallel, the task of obtaining plutonium-239, which does not exist in nature, was being solved. It could be synthesized by irradiating uranium-238 in special reactors. For this, the first industrial nuclear reactors in the world were built at Hanford, Washington. They were massive structures with graphite stacks, inside which controlled nuclear reactions took place. The irradiated uranium blocks were then sent to processing plants, where plutonium was extracted from them. The chemical process was extremely complex and dangerous. Workers faced high levels of radioactivity, and the technologies had to be developed literally on the fly. But thanks to these reactors, the first grams of plutonium were obtained, and by 1945 kilograms, sufficient to assemble an implosion-type bomb. The production of materials was accompanied by numerous difficulties. First and foremost were engineering problems. Uranium enrichment installations often broke down, chemical processes at Hanford yielded unpredictable results, and personnel had to work under conditions where science itself did not yet have ready-made solutions. The second difficulty lay in the human factor. Tens of thousands of people worked at the plants without knowing what exactly they were doing. They were told only that their work was important for victory, but the true goal remained hidden. Secrecy was so strict that even many engineers and scientists had access only to part of the information. Equally important was the issue of raw material supply. The reserves of uranium ore from the Belgian Congo, which were secretly purchased and transported to the United States, played a key role. Without these supplies, the production of uranium-235 would have been practically impossible. Thus, the Manhattan Project encompassed not only scientific laboratories and industrial enterprises but also a complex international network for extracting, transporting, and guarding strategic raw materials. The result of these efforts was that by 1945 the project had at its disposal two types of fissile materials in quantities sufficient to create combat-ready designs. Uranium-235 was used in the Little Boy bomb, and plutonium-239 in the Fat Man bomb. But it must be remembered that behind every gram of these substances stood months of work by thousands of people, tens of billions of kilowatt-hours of energy, hundreds of tons of processed ore, and a strain previously unknown to science and industry. Thus, the production of materials became not only a central stage of the Manhattan Project but also one of the greatest industrial feats of the Second World War. For the first time, humanity created an entire sector aimed not at serial production of mass goods but at obtaining tiny quantities of the rarest substances whose destructive power was comparable to the forces of nature. When the Manhattan Project obtained the first batches of uranium-235 and plutonium-239, it became clear that the key task still lay ahead. It was necessary not only to confirm theoretical calculations but also to ensure that the materials behaved predictably under conditions as close as possible to combat use. Laboratory testing became the main tool for verifying hypotheses and finding solutions to numerous technical difficulties. However, this stage was accompanied by challenges no less significant than the production of fissile substances itself. One of the first problems was the unpredictability of plutonium's behavior. Initially, it was assumed that it could be used in a gun-type scheme similar to the uranium one. However, during experiments it became clear that plutonium produced in reactors contains impurities of the isotope plutonium-240. It had a high tendency to spontaneous fission, due to which the reaction could start prematurely, destroying the charge before the full effect was reached. This feature made the gun-type scheme completely unreliable and forced scientists to focus on the implosion design. But implosion was far more complex. To implement it, a system of simultaneous detonation of dozens of detonators was required, which in terms of precision and technological demands went far beyond known methods. Los Alamos turned into a center of intensive experiments. Work was carried out there on modeling explosions, checking mock-ups made of inert materials, and studying shockwave behavior. Particular attention was paid to symmetry. The slightest misalignment during the compression of the plutonium core rendered the scheme inoperative. Dozens of tests were conducted to verify this, many of which ended in failure. Scientists faced the fact that the results of calculations did not always coincide with reality. Explosive dynamics turned out to be too complex for the computational methods of the time, and researchers had to proceed by trial and error. Safety problems also arose. Working with fissile materials posed a mortal risk, since even a small mistake could lead to an uncontrolled chain reaction. Critical experiments were conducted in Los Alamos tests to determine the conditions under which a mass of material becomes dangerous. One such experiment ended in tragedy. In May 1946, already after the war, physicist Louis Slotin died as a result of an accident with a plutonium sample when the reaction went out of control. These incidents clearly showed how dangerous the very nature of the processes under study was. Another serious difficulty was the creation of detonators and synchronizing devices. The implosion scheme required the simultaneous operation of explosives with precision down to millionths of a second. Any deviation in the operation of even a single detonator led to the failure of the entire design. To solve this problem, new methods of electrical initiation were developed, many prototypes were created, and hundreds of tests were carried out. Only by mid-1945 was the required synchrony achieved. guaranteeing successful compression of the plutonium core. Psychological aspects also played an important role. Many of the scientists, who had come to the project from the university environment, encountered for the first time the necessity of working under severe deadline pressure and in conditions of complete secrecy. Errors were felt painfully, each failure delayed overall progress. But it was in this atmosphere of tension that a unique work culture took shape. Intensive seminars, night discussions, and joint experiments became part of everyday life in Los Alamos. Thus, the laboratory tests of the Manhattan Project were not just a technical stage but a true school of practical mastery of new physical phenomena. They revealed the limitations of the initial ideas, forced the abandonment of the gun-type scheme for plutonium, and led to the creation of a most complex implosion design. They required the development of new instruments, measurement methods, and approaches to safety. And although this stage was accompanied by failures and tragedies, it made possible the transition to the final test, the first nuclear explosion, which was to ultimately confirm the viability of the solutions created. On July 16, 1945, in the Jornada del Muerto desert of New Mexico, the first nuclear explosion in human history took place, codenamed Trinity. This event became the culmination of years of work on the Manhattan Project, after a series of laboratory tests, calculations, and the production of an experimental device. The decisive practical confirmation of the developed solution's viability had arrived. Preparation for Trinity was carried out with the utmost thoroughness. Observation posts were erected at a remote site, meteorological services calculated winds and atmospheric stability, and numerous instruments were installed to record light, pressure, radiation, and seismic effects. Safety measures were worked out in case of unforeseen consequences. Strict restrictions on movement and access were in force in the surrounding areas. The test device was an implosion-type unit assembled from materials produced within the project. It was raised on a concrete tower to simulate the conditions of an airburst and to collect data comparable to the expected parameters of combat use. Hundreds of observers were present on site, leading scientists, engineers, and military personnel, including J. Robert Oppenheimer and General Leslie Groves, who monitored the operation from specially equipped shelters at a distance. The anticipation was tense. Many understood that the result of the test would have not only technical but also historical, political, and ethical significance. At the appointed time, the device was detonated. An instantaneous flash lit the desert brighter than the sun, and then an impressive mushroom-shaped cloud formed, rising kilometers into the sky. Instruments recorded a powerful shock wave and the release of a huge amount of energy. A crater formed on the surface, along with patches of fused, glassy material later called trinitite. Estimates of the explosion's yield were about 20 kilotons of TNT equivalent, a figure confirmed by subsequent calculations and measurements. For the scientists, this meant that the implosion scheme was workable and that a properly executed plutonium charge produced the expected effect. The reaction of those present was mixed. On the one hand, scientific triumph, the confirmation of the work done and the proof of theoretical models' correctness; on the other, profound moral shock. According to eyewitness accounts, many participants experienced complex feelings, from the elation of professional success to anxiety and an awareness of the destructive power of the device they had created. Later, Oppenheimer recalled a line from the Bhagavad Gita that came to mind at that moment: "Now I am become death, the destroyer of worlds," which became a symbolic expression of the achievement's dual nature, the greatness of science and the weight of responsibility at once. The analysis of Trinity's data had immediate consequences. Confirmation of the explosive effect accelerated decision-making at the highest level regarding the readiness of warheads and the possibility of their use in wartime conditions. The test also made it possible to collect the most important empirical data necessary for further refinement and standardization of designs, as well as for assessing consequences under various application scenarios. In the U.S. military and political leadership, Trinity was perceived as final confirmation that nuclear weapons represented a real strategic force. At the same time, the test raised a number of new questions: technical, environmental, and ethical. The consequences of radioactive contamination, the long-term effects on the environment and people, and the moral responsibility of the scientific community became the subject of subsequent discussions and debates. Trinity left tangible evidence, patches of fused soil, instrument records, and participants' recollections that helped historians, engineers, and policymakers assess the scale and nature of the event. Thus, Trinity was not merely a scientific experiment, it was a historical event that marked a new stage in the development of technology and international politics. The test confirmed the technical feasibility of nuclear weapons and opened a new, grave page in the history of the 20th century, a page in which scientific discoveries and state strategy proved inseparable, and the consequences of decisions were irreversible and global. After successful laboratory testing in Trinity in mid-July 1945, the U.S. military and political leadership faced a practical question: how and when to use the weapon that had been created. Preparation for use simultaneously involved political decisions, operational tactical organization, final assembly of warheads, crew training, and detailed refinement of safety procedures. These elements were interconnected and carried out under conditions of strict secrecy and limited time. The political side of the process had several key channels. In May-June 1945, the Interim Committee, created by the Secretary of War, studied options for use and recommended combat deployment without prior warning if necessary to bring the war to a rapid end. This recommendation became one of the official bases for subsequent operational orders. It was also supported by the project's scientific advisors. Meanwhile, at the international level, the Allies formulated an ultimatum to Japan. The Potsdam Declaration of July 26, 1945, declared that the alternative to surrender was prompt and utter destruction. These political steps created the framework within which practical decisions were made. Operational preparation focused on several areas. First, an aircraft platform and crews capable of delivering and safely dropping the bombs were needed. To this end, B-29 bombers were modified under the Silver Plate program. The aircraft received reinforced bomb bays, special suspensions, and other changes that made it possible not only to carry unusual payloads but also to fly long distances reliably. The specially formed 509th Composite Group included trained crews who underwent detailed preparation in tactics, navigation, and procedures for handling the weapon. Second, the final formation of the warheads and their assembly in field conditions was required. The munitions, both the uranium device, Little Boy, and the plutonium one, Fat Man, were delivered to the airbase on Tinian Island in the Pacific, where final assembly, mechanical checks, and preparation for loading onto aircraft were carried out. All this took place under military control, with refined procedures of secrecy, security, and verification to exclude accidental loss or disclosure. In some operations, such as the final preparation of the uranium gun-type design, maximum precautions and restricted access were enforced. Particular attention was paid to target selection and the criteria for choosing them. Expert commissions and the Los Alamos Target Committee formed a list of cities suitable for demonstrating destructive power, military and industrial significance, building density, the fact that the city had not previously been heavily bombed, so the effect could be unambiguously assessed, as well as humanitarian and cultural considerations were taken into account. Initial candidates included Hiroshima, Kokura, Nagata, Kyoto, and others. In the course of political and service discussions, some were excluded or placed in reserve. Finally, a strict chain of decision-making and reporting was in force. After Trinity, technical leaders confirmed the readiness of the implosion scheme, the military issued orders to prepare the missions, and the political leadership received summaries and recommendations. Given weather, intelligence, and operational conditions, final orders regarding takeoff times and target choice were made on Tinian. The result of this complex process was the combat sorties of August 6 and 9, 1945. But the decisive stage, a combination of political recommendations, crew training, aircraft modifications, secret assembly, and target selection, was completed within a few weeks after Trinity. Thus, preparation for the use of nuclear weapons was a combination of political decisions, institutional procedures, and detailed technical organization. It was a multifaceted process in which every component, from moral assessment and diplomacy to the last bolt on the aircraft, was critical to ensure that the objectives were achieved quickly and under conditions of confidentiality. The morning of August 6, 1945, began as another sortie from the Pacific base on Tinian, but for the crew of the B-29 Enola Gay and the accompanying aircraft, it was a mission of exceptional character. The aircraft under Colonel Paul Tibbets took on board a live uranium gun-type warhead, Little Boy, and took off together with two auxiliary planes tasked with observation and data recording. The bomb was finally armed in the air, a procedure devised specifically to reduce risks during takeoff. The arming and sequence of actions on board had been worked out in advance. The crew acted in strict accordance with mission instructions. At 8:15 local time, Little Boy was dropped over Hiroshima. The bomb fell for about a minute and detonated at an altitude of approximately 9,800 feet, 580,590 m, above the target area, an airburst calculated for maximum effect on dense urban development. The explosion was accompanied by a blinding flash, followed by a shock wave and fires that instantly destroyed the central districts of the city. By modern estimates, the yield of the blast was comparable to 1,520 kilotons of TNT. The radius of total destruction was about a kilometer, with fires covering a significantly larger area. The effect was not only mechanical. People in the epicenter or nearby received fatal injuries not only from the shock wave and debris but also from intense thermal radiation and subsequent fire. Numerous buildings were completely destroyed or ignited. Panic arose in the streets, many victims suffered severe burns and injuries, and the medical system was unable to provide emergency aid on such a scale. By the end of 1945, the number of deaths in Hiroshima from the immediate consequences of the bombing and from radiation effects is estimated in the tens of thousands. Several tens of thousands died in the first hours and days alone. 3 days later, on August 9, the aircraft Boxcar carried out the mission to deliver the plutonium implosion warhead Fat Man to Nagasaki. The planned primary target, Kokura, was covered by dense clouds and smoke, so the crew switched the attack to the secondary target, Nagasaki. The bomb was dropped in the morning and detonated at an altitude of about 1,650 feet, 500 meters, producing an explosive yield close to 20 kilotons. Due to the hilly terrain and partial cloud cover, the destruction over the same radial area was less uniform than in relatively flat Hiroshima, but no less catastrophic for the city and its population. The immediate human losses and long-term consequences included not only those killed and injured by the blast but also those who later died from injuries and illnesses associated with radiation exposure. In addition, the destruction of infrastructure, water supply, medical services, transportation exacerbated the crisis and made evacuation and aid extremely difficult. These events had a decisive impact on the further development of the conflict. In combination with other political and military factors, they became one of the drivers leading to Japan's capitulation and the end of the Second World War in Asia. At the same time, the bomb's use opened a new era in international politics and security, generating ongoing debates about the moral and legal aspects of their use, as well as the humanitarian and environmental consequences of nuclear weapons. The emotional reaction of mission participants and observers was complex and contradictory. Many of those present noted both a professional sense of completing the task and a deep moral shock at the destruction and human tragedy they witnessed. Documentary materials, records, and recollections from those days provided historians and society with material for long reflection on the price of scientific and technological achievements translated into military practice. Today, the memories of Hiroshima and Nagasaki remain a powerful reminder of the destructive power of nuclear weapons and the need for international efforts toward non-proliferation and the reduction of nuclear risks.